This topic is the squeeze theorem for limits. The squeeze theorem is a powerful tool for finding a limit of a function that is difficult to evaluate directly. It works when the function is trapped between two other functions whose limits at a point are known and equal. Intuitively, if a function is squeezed between two functions that are both approach the same value, it must approach the same value. So what are we doing here? Really what we have is one function that's being a really big pain. Maybe that function oscillates and we don't exactly know what's going on, and we want to know what's happening at this point right here. The trick is, if this is our function f of x, that we find a different function that's below it, smaller than it, g of x. Maybe it looks something like this, and it's a nice function that we know something about. Then we have another function above it, h of x, looks something like this right here, and we know about that one. And the idea is, if h of x is always bigger than f of x, and g of x is always smaller than f of x, and we know that these two functions both have the same limit at this value, then that middle function, that trapped function, also has to have that same value. So if you have g of x, which is always, the blue function is always smaller than f of x, the red function, which is always smaller than h of x, so that red function's trapped. And we know that the blue function and the green function in this case have the same limit, then that red function has to converge to that one. So what's the trick? It's to find the function that's always bigger and the function that's always smaller that converge to the same thing. This is absolutely key. The bigger function and the smaller function converge to the same thing. Then you can make that conclusion. So that's a visual idea of what's going on with the squeeze theorem. F of x is literally squeezed between these two functions. So how do we do it? First of all, find the function that you're trying to find the limit of. It's the one that's the pain, the red function. Now you're going to find the two bounding functions, the one that's smaller than it, the one that's bigger than it. Find out what those limits are. Those limits do need to exist, and they need to be equal. Okay, we want those to exist, and they need to be equal. Then we're going to make a conclusion. By the squeeze theorem, we can conclude that the function of our red function, our pain in the butt function, that one exists, and it's equal to the same number. Let's give it a try. It's going to be easier in practice than it is discussing it conceptually. It says, suppose that the following is true. 3x plus 5 is less than or equal to g of x is less than or equal to x cubed plus 7 for all x in the interval 0 to 2. So here we have a smaller function. That blue function is the 3x plus 5. That's our lower function according to that picture right there. The bigger function, the green function, would be the x cubed plus 7. So this g of x is sandwiched in between those two functions, the smaller and the big function. Okay? The idea is we want to evaluate the limit of that middle function, that pain in the butt function. Well, what we know, if this is true, this statement right here, this inequality is true, and because x equals 1 is in that domain that we're talking about here, that is, we are talking about this function, it's true at this point, then we know that this must be true. The limit as x approaches 1 of the blue function, 3x plus 5, has to be less than or equal to the limit as x approaches 1 of that middle function, which has to be less than or equal to the limit as x approaches 1 of the green function, that bigger function, that x cubed plus 7. So if that inequality is true, then that inequality must hold true also with the limits. Okay, let's keep on going then. So each one of these limits we're going to evaluate individually, and we're just going to use direct substitution. So we know that the limit as x approaches 1 of 3x plus 5 should be equal to 3 times 1 plus 5, which is a value of 8. Okay, so that blue one right there is going to be the value 8. Let's look at the next one. The limit as x approaches 1 of the right-hand side, which was x cubed plus 7. We're going to use direct substitution. Plugging it in, we would have 1 cubed plus 7, which is also equal to 8. So this green function right here, we know that its limit also approaches 8. So right now we have 8 is less than or equal to the limit as x approaches 1 of g of x is less than or equal to 8. Notice that tells us by the squeeze theorem, I'm just going to put th in for squeeze theorem, we can conclude that the limit as x approaches 1 of g of x has to be the same value, which is 8. The lower one goes to 8, the bigger one goes to 8, so the middle one has to go to 8 as well. Okay? When they give you the functions, this is really easy. All you got to do is direct substitution, plug in the number. Hopefully you get the same number here. Like here in this case we had 8 is less than or equal to g of x is less than or equal to. We're good. We're done. Okay? What if they don't give you the lower function and the bigger function? It's really hard to determine what's the lower function and what's the bigger function in general, but this is a theorem that is very, very useful. Look at this function right here. We want to calculate the limit as x approaches 1 of the quantity 1 minus x, that quantity raised to the fourth, times the sine of the quantity 1 over 1 minus x plus 3. This is a nasty, nasty function. And notice if I plug in the number 1, I would have 1 minus 1 in the denominator here, so this would be the sine of 1 over 0. Well, that's undefined. Because it's undefined, the function doesn't exist at the point. When the function doesn't exist at the point, that doesn't mean that the limit doesn't exist at that point, so we have to do a deeper level of analysis. We can't just say the limit doesn't exist because when you plug in 1, it doesn't exist. We have to do a deeper level of analysis. So this is going to come back to some other knowledge. First of all, you should know that the sine of x, when you look at that function, has a range of -1 to 1. The only values that can come out of sine is between -1 and 1. And if you remember the graph of sine, you can remember that it's bound between -1 and 1. So that's my range, that's the y value. So no matter what, whatever number comes out of here has to be between -1 and 1. In fact, let me write that down. We know that -1 has to be less than or equal to sine of 1 over 1 minus x, which is less than or equal to 1. It is bound between -1 and 1 because it's one of our trig functions. That's its range. That's a true statement no matter what the x value is. Well, with inequalities, remember we can multiply by whatever we want or divide by whatever we want. Unless it's negative. If it's negative, we do need to flip the inequalities. But in particular, what I want you to do is I want you to look at this. Think about 1 minus x raised to the fourth power. 1 minus x raised to the fourth power, because we have an even power, no matter what it is, if you put a negative number to an even power, or if you put a positive number to an even power, that number is always positive. It's always positive, right? So this term right here is always positive. Because it's always positive, I can multiply every point of my inequality times that number. In other words, I could say -1 times 1 minus x to the fourth has to be less than or equal to 1 minus x raised to the fourth times the sine of 1 over 1 minus x, which has to be less than or equal to 1 times 1 minus x to the fourth, the quantity 1 minus x raised to the fourth. So all I did literally was just took every single one of these terms and I multiplied it by a positive number, 1 minus x to the fourth. And now also, remember with inequalities, I can add or subtract whatever I want as long as I do it to every part of the inequality. So in particular, I want to do it to, I want to add 3 to every single one of these. So simplifying that, on the left-hand side, I would have negative, and I'd have my 1 minus x to the fourth, quantity 1 minus x raised to the fourth. I'm just going to add 3 to the left-hand side of the inequality. Well, I can do that as long as I take the middle of the inequality, which is the quantity 1 minus x raised to the fourth, times sine of 1 over 1 minus x. I have to add 3 there. And then I also have to add 3 to the right-hand side of the inequality. So I'd have 1 minus x raised to the fourth, and I'm going to add 3 there. So again, in this one, we're going to multiply all by 1 minus x raised to the fourth. We can do that because it's positive. On this one, we're going to add 3 to all of them. So that's what we did between those steps. And now, notice we have a lower function. We have a higher function in our middle function. So this would be f of x in the squeeze theorem. This one would be g of x, and this one would be h of x. We have three different functions here, and we have one function that's bound by the other two. So if this inequality is true for all x, which it is, then we know that the limits of these functions has to be true as well. So in other words, what we know has to be true is the limit as x approaches 1 of the left-hand side, which was a negative, 1 minus x quantity raised to the fourth plus 3. That has to be less than or equal to the limit as x approaches 1 of the middle one, which was our original function, 1 minus x raised to the fourth, of sine of 1 over 1 minus x, that quantity plus 3. And that has to be less than or equal to the limit as x approaches 1 of the right-hand side of the inequality, which was 1 minus x raised to the fourth plus 3. Okay? So in this one, we added the limit as x approaches 1 to all. That's what we're doing to get to that step right there. Right? This is our goal. This is the original problem right here. This is the original problem. I'm going to evaluate each one of these limits right here because those are polynomial functions. I'm going to evaluate them with direct substitution. So if I come in here and I want to evaluate just this right here, this would be a negative. 1 minus 1 raised to the fourth power plus 3. Notice when I do that, 1 minus 1 is 0, 0 to the fourth is 0, plus 3 would be a 3. I'm going to do the same thing here. I'm going to look at this function. I'm going to evaluate it directly. Okay, so when I do that, it would be 1 minus 1 raised to the fourth power plus 3. That's 0 to the fourth, which is 0, plus 3, which is 3. Notice now that I have the left-hand side, which was 3, is less than or equal to the limit as x approaches 1 of my original problem, the 1 minus x, quantity raised to the fourth, the sine of 1 over x, 1 minus x, plus 3, and I know that that has to be less than or equal to the right-hand side, which was 3. So what's happened? I've squeezed that term in between two other limits that I do know and I can calculate. By the squeeze theorem, what we know is that this limit has to be the same, a value of 3. We've trapped it. It's trapped between 3's, so we know the limit has to be 3. So really, really tricky on that one. You're going to have several problems that are very similar to this. I know this write-up looks a little weird, so I hope you understood it in the video. Again, the idea is by taking this trig function right here, which will be a sine or a cosine, we know that's always going to be bound by -1 or 1. We're going to multiply each term by this. The only reason we can do that without changing the inequalities is because we know that is always positive. So we multiplied all 3 terms by that. Then we added the last piece. We added 3 to all 3 of those terms. Now we have our original function bounded between 2 functions. So we find the limit of those outside 2 functions. Because those limits were the same, the one that's smaller is 3, the one that's bigger is 3, the one in the middle has to be 3. So there is a nice, advanced, difficult example of the squeeze theorem. Okay, an easy example where the functions are given to you, and another one where you actually had to find them. I hope that helps.